would like to tell now a small case study how can we use the Laplace equation. We can already do something. It is the problem of attraction of a ball. So we know that our planet is a ball, and by the Newton's law it attracts. So how can we evaluate its attraction force? So we have this planet, it's Earth or other planet, and there exists a thing which is called the gravity potential. Gravity potential, let's say phi of x1, x2, x3, or phi of x in R3. And the force which acts on a small piece of matter with mass m, F equals minus m times gradient phi. What else is known about this phi of x? It is known that phi of x satisfies the following Poisson equation. Phi Laplacian phi of x equals rho of x. Here rho is the density. Now, principle there is a constant depending on the units. We can choose a constant which is choose the unit such as this constant is 1. So we are working in the non-dimensional situation. So we have this equation which is Poisson equation. And suppose we have a planet, again, I write you. Here it is in the origin, yes, and rho of x equals the following: 1 if module x is less than 1. The radius of this ball, suppose it is 1, and 0 if module x more than 1. Now, here I did not write what happens when module x is equal to 1, but it is not material. It is just a layer of 0 thickness on the surface of the planet, so it does not change anything. So we are solving this equation in the whole space. Laplacian phi is rho of x, where rho x is this. How to solve it? No, our situation is spherically symmetric. We can rotate this ball and nothing changes because its density is constant inside the ball. So this means that the gravitational potential phi of x depends in fact on distance from the origin of module x, no, some function v of module x. Yes? And now if you have a function which depends only on the distance from the origin, then Laplacian phi also is a function of x. equals the following: v double prime of r, v of r. R is module x. V double prime of r plus 2 divided by n v prime of r. Yes? 2 divided by r. So, why so? Because we already derived a formula which works in any dimension. In Rn, if phi of x equals v of module x, v of r, then Laplacian phi equals v double prime of r plus n minus 1 divided by r v prime of r. Yeah. So we have this general relation, and in particular in three-dimensional case n minus 2 equals n minus 1 equals 2. So we have this equation. And we have to solve our equation in the case when rho of x, so our equation is v double prime plus 2 divided by r v prime equals f of r, where f of r equals 1 if r less than 1 and 0 if r more than 1. No, r is positive, so I don't write that this more than 0. No, this problem splits in two problems. One is for r less than 1 and other for r more than 1. R less than 1. So then you have 1. V double prime plus 2 divided by r v prime equals 1. We have this equation. It is ordinary equation, and we can easily define its particular solution. Particular solution of non-homogeneous equation of r, if you substitute here, say, r square, some constant times r square, yes, then vp double prime plus 2 divided by r vp prime equals second derivative is 2c plus 2c for 2 divided by r times 2c r equals, all in all, 6c. Yeah, this r cancels this r, and this should be equal to 1. So c equals 1/6. And now the general solution of homogeneous equation Vp of r. Let us see. It is no. Let me guess that is some power of r, and power should be minus 1. So C1 r minus 1 plus C2. Now about C2, any constant, of course, is solution of homogeneous equation. And about C1 r minus 1, why? It's because Vp double prime plus 2 over r Vp prime, yes, Vc, it is complementary solution, equals minus 2 C1 r minus 1 minus 3 plus no, why minus? Plus 2 C1 minus 2 divided by r times 1 over r square. Yes, which is 0. Yeah, so this term gives a solution of homogeneous equation, and this is, of course, V of r equals r squared divided by 2 plus C1 r minus 1 plus C2 if r less than 1. Now if r more than 1, in this case we have a homogeneous equation V double prime plus 2 over r V prime equals 0, and remains only solution of homogeneous equation. So V of r equals C1 and C2 C3 r minus 1 plus C4. So we have these two solutions. Now they should be somehow related to one another. And relation is the following. If you consider the value of solution from the point 1 minus 0, I mean I take this solution and substitute here 1. So we continue this to the point r equal 1, it is 1 minus 0, so we go to the left, equals r squared over 6, 1 6 plus C1 r minus 1 plus C2, C1 plus C2. V prime of one moment. I want to exclude some terms here from the beginning. First of all, solution, this term, goes to infinity when r goes to 0. So it is non-physical. There is nothing singular at the center of the ball. Yes, there is. It would go to infinity if there was a point mass at the center. If there is no point mass, so there is no singularity. So we have to conclude that C1 equals 0. Now, if you look at this, we have this constant C4. In fact, we can add to the potential a constant, arbitrary constant, and the force will not change, because the force which acts on any test body depends only on the gradient of the function phi, not on the value of phi. So the value of phi itself has no physical meaning. So we can choose this constant, and let us choose is like this. C4 equals 0. So this means that V of R goes to 0 as R goes to infinity. Yes? So we have V of R, after all, equals R square over 6 plus C2 if R less than 1, and equals C3 R minus 1 if R more than 1. So we found this function V. Now the first thing that this function should be continuous. Yes? So this function should be continuous because otherwise we have the force has some delta function on the boundary of the ball, and this does not happen. So V of 1 minus 0 equals V of 1 plus 0. Moreover, it should be its derivative should be continuous. No, again, because if you imagine that you stay on the surface of this ball, you are attracted to the ball, yes, and now you dig a hole of some depth, yes, a well, and if you go down the well, you don't notice any change of attraction to the center. Yes, if you take a pail and descend it into the well, yes, the weight of this pail does not change when you cross the surface of the earth. So this means that V prime of 1 minus 0 equals V prime of 1 plus 0. So we have these two conditions. So the right hand side, the function f of r, is discontinuous, but solution is continuous and its derivative is continuous, because solution of ordinary equation of second order is 2 units more regular than the right hand side. If right hand side is just bounded, then solution is continuous and its derivative is continuous. And its second derivative is also bounded. It is true for any linear second order equation, ordinary equation. Now, so what we have? V of 1 minus 0 equals 1/6 plus C2. V prime of 1 minus 0 equals derivative 1/3. That's it. V of 1 plus 0 equals C3. V prime of 1 plus 0, we have to differentiate it. It is minus C3 R minus 2, R equals 1. It is minus C3. And so we have the following equation to define the constant C2 and C3. 1/6 plus C2 equals C3. 1/3 equals minus C3. From here we have C3 equals minus 1/3. Yes. C2 equals C3 minus 1/6. It is minus 1/2. And after all, we have the following solution. This solution. V of R equals R squared divided by 6 minus 1/2. If R less than 1. And if R more than 1, it is minus 1/3 R minus 1, R more than 1. Yeah? And the potential phi of x equals V of module x. So what does it give us? So this is our ball. This is, say, x-axis, no, x1 axis, yes? And we want to measure the force. So we put a test particle, small particle, at different distances from the center of this ball. No, we can even put it inside the ball, say we bore a hole here in the ball, like this, up to the center. And we can even put this particle inside, or we can ball it through the whole, the hole goes through the whole ball. And the particle can be put both inside this hole and outside. And so what is the force? So F equals, M, it's mass of these particles, no, it is maybe, I think usually small things, times gradient phi. Gradient phi is directed along the radius vector, because phi is function depending only on the radius, radial function. Yes, so let me, if I move along the x1 axis, equals m times d v d x1, but here we have to put the minus sign. So we are moving in the direction, the force acts in the direction of decrease of potential. So it is minus m dv dx1. And so what we have, F equals minus x1, module x1, divided by 3 if module x1 less than 1. And it is equal minus m divided by x1 square, yes, x1 square, I'm sorry, like this. If model x more than 1. No, I would say it is for positive x1. Let me write if we want to accommodate for both values of x1. So here it is like this, x1 divide model x1 cube. Yes, because we have to have here it attracts to the ball in this direction, here attracts in this direction. So we have to write this way. That's it. So if we are inside the ball and move in this hole, then the force is proportional to the distance from the center and directed to the center. So this means that our small particle will move forth and back here like a pendulum, like a linear oscillator. Yes? And no, to make it work, we have to first drill this hole from pole to pole, so that remove the action of rotation of the ball, which is our Earth, and second, remove all the air there, otherwise it will stop eventually. And here, this is the usual attraction of test particle to the ball. This is a Newton law of attraction, which acts outside of the ball. Now, this is a small example, but I would like to say that this simple thing which I have derived costed Newton, as much as I know, about 20 years of work, because he had to develop all the machinery of calculus to solve this problem, and he solved it by far longer and more straightforward thing. He simply integrated the force which was produced by all small particles in the ball on this test particle, and proved that the force is the same as if all the mass of this ball was at the center. It was a great feat of Newton, and now you see with this already what we have already, which is a very, I would say, small part of apparatus of equations, we have solved this problem so easily. So it was just a small, I would say, example of how it works. No, hopefully we'll have more. For now, let us finish. Have a good time. Bye.